Now let's talk about the deep circulation in the ocean. We know the deep ocean must circulate. We know this because of the distribution of traces, particularly man-made traces, and by the distribution of nutrients that aren't recycled, so primarily nutrients from skeletons. So let's start by looking at the tracer tritium. So tritium doesn't really exist in nature, but it's a byproduct of nuclear weapons. Released in the atmosphere by the atmospheric nuclear testing. In 1962, the Comprehensive Test Ban Treaty came into effect, which prevented atmospheric nuclear testing. So in the lead up to that, there was a lot of nuclear bombs set off in the atmosphere, and then that sent material way up into the stratosphere, and this tritium eventually, a couple of years later, made it back down into the troposphere where it could get into rain. So what's in this plot here is the tritium rainfall over Ireland on the vertical axis and the year in the 19th century on the horizontal axis. So 1952 up to 1974. And you'll notice that around 63, 64, there is this massive peak in tritium from the atmospheric tests 2 years before that. So that tritium fell all over the North Atlantic. And what we have here in these two plots is the distribution in the North Atlantic versus depth. So the vertical axis is depth, horizontal axis is latitude, 10 degrees south, equator, and then almost towards 80 degrees north. And so we have two time periods here, 1972 on the left and 1981 on the right. And the contours are in tritium units, which sort of an arbitrary unit. And so the sort of mauvey color is one tritium unit, and the bluey color is the two tritium unit contours. So you'll see that in 1972, there is tritium over the entire surface, but it's getting deepest in the North Atlantic here. So, gets down to almost 5,000 meters. 9 years later, there is more tritium in the deep ocean, but again, it's all coming down from the North Atlantic rather than directly down from where it's been at the surface in the tropics. Okay, so now let's look at silicate. So this is a nutrient that's used for building skeletons. And as such, it's not recycled in the same way as the nutrients for soft tissues. That when an organism dies, the soft tissue nutrients are recycled primarily in the mixed layer or in the photic zone, and then somewhat in the layer below that, the no-light layer. Whereas the silicate falls through the ocean and gets into the deep water and eventually into the ocean sediments. So what's shown in this picture is the ocean basins below, I think, around 3,500 meters depth. So they do look kind of weird. Here we have the Atlantic, the mid-Atlantic ridge through the middle, Southern Ocean, Indian Ocean, Australia, New Zealand, North America, east coast of Asia. So this is the Pacific Basin. And the contours here are the concentrations of silicate in the bottom waters. So you'll see that they start in the North Atlantic around 20, 40, 60, 80. By the time you get to the Southern Ocean, 120-ish. And then as you move up in towards the North Pacific, they increase to 160. So what's this telling us? Well, this water in the North Atlantic has had less rain down onto it. By the time it gets to the North Pacific, it's accumulated more. So this could tell us the age of the water, that the deep water in the North Atlantic is younger than the deep water in the North Pacific. Reiterating that, so tritium lands over the entire North Atlantic Ocean, but is only found in the polar regions, at least initially. and silicate concentrations are lowest in the North Atlantic and highest in the North Pacific. So the silicate indicates that the water in the North Pacific is older. So this is suggestive of our deep water circulation, that the deep water has been formed in the North Atlantic in contact with the atmosphere, and that there's no deep water formation in the North Pacific. Otherwise, the silicate concentrations there would be much lower. So it's reasonable to assume that there is this circulation between the North Atlantic and the North Pacific. So this is a good start to understanding the deep ocean circulation, but it's not the whole story. So we know that temperature and salinity are set at the surface of the ocean through atmospheric interaction. So either solar radiation, heating the water, winds and evaporation, cooling the water, precipitation adding fresh water, and evaporation taking away fresh water. We also saw in the last video that the density stratifications are weaker at the poles, so there's a lot less difference between bottom and surface, the pole, in terms of density compared to the tropics or even the mid-latitudes. So this makes it more likely that the deep water and the bottom water will form in the polar regions where you have this weaker stratification. So here, by bottom water, I'm talking about water that's in contact with the bottom of the ocean, and deep water is water that can also be in contact with the bottom of the ocean, but it would sit on top of any bottom water. So the two that we're going to talk about primarily are North Atlantic deep water and Antarctic bottom water. So this is a plot of the density of the surface ocean. The dark blues are higher densities, the light white colors are lower density surface water. So you'll notice that the reddy circles highlight some of the deepest or the densest surface water. So North Atlantic and around Antarctica. This green one shows that there is dense water in the Mediterranean as well. But importantly, for the deep circulation, and along with what we saw in the silicate distribution, there is no dense water, dense surface water in the North Pacific, so there can't be any deep water formation in the North Pacific. So let's talk briefly about the Mediterranean, which was highlighted in green on the previous slide. It is the saltiest water on the planet, but it's not very cold. So it's salty because the Mediterranean is an area where evaporation exceeds precipitation. And so Atlantic water, which is relatively fresh, flows into the Mediterranean. A lot of the evaporation happens, so the water becomes saltier. That saltier water flows back out through the Strait of Gibraltar underneath the incoming Atlantic water, but the Mediterranean water is too warm to sink too deep. Certainly can't sink below the North Atlantic deep water. And it turns out it spreads out at about 1,500 meters depth. So here we have salinity at 1,500 meters deep. So we have high salinity in the Mediterranean here, and then this tongue of high salinity spreading all the way out across the North Atlantic Ocean, but doesn't really sink below 1,500 meters. So the majority of the deep water and bottom water forms either in the North Atlantic or around Antarctica. So here, Antarctica is on the right-hand side, so 80 degrees south, the equator here in the middle, and the northern latitudes over here, depth on this axis. So the Antarctic bottom water, and then flows along the bottom. The North Atlantic deep water forms in the North Atlantic, flows along the bottom, but when it gets to a region where there's Antarctic bottom water, it flows across the top of it because it's not as dense as the Antarctic bottom water. North Atlantic deep water is formed when warm, salty water travels north, so the Gulf Stream, which we'll talk about in a subsequent video. And during winter, the water cools and sea ice forms. So primarily seasonal sea ice, and then that can become long-term sea ice. When sea ice forms, the lattice structure doesn't allow the salt to be in there, so the salt in the salt water is rejected when sea ice forms, and you get this, what's called brine rejection. You get very salty water coming out from underneath the ice. And as that is cool and is also salty, that is very dense water, and it sinks. And this happens in the Labrador Sea and the Greenland Sea in the North Atlantic. Antarctic bottom water is primarily formed in the Weddell Sea and Ross Sea. So similar mechanism. So again, sea ice formation drives the salt out, so you get salt, more salty water. What happens in the Antarctic that doesn't happen in the North Atlantic is there's a continental shelf there. So a lot of the dense salty water falls to the shelf, continental shelf, and not all the way down to the bottom of the ocean, the deep ocean. And so as it sits there on the shelf, it gets colder and colder because it's saltier. It can get below 0 degrees because it's salt water. And so once it's got very cold, then it can flow down, it gets over this and down the slope. And then you get this very cold, salty water that flows along the bottom, and the North Atlantic deep water is not as dense, so it flows above that. There are sort of a number of schematics of what this deep ocean circulation looks like. A popular one, which is a gross oversimplification, but it does get across some of the key points, is what's known as the Great Ocean Conveyor Belt. So we have, in this case, it's North Atlantic centric. We have surface water, the red ribbons, coming up in the North Atlantic, sinking in the North Atlantic and becoming bottom water, the blue, and then it flowing around into the North Pacific, coming back up, flows into the Northern Indian Ocean, comes back up. So this is a highly simplified but relatively informative schematic. On average, it takes a water parcel around 1,000 years to complete this cycle. So that could be considered the stirring time of the ocean. So this deep circulation is sometimes called the meridional overturning circulation, and this is because it's transporting heat primarily across latitude bands. It's also sometimes called the thermohaline circulation, and this is because it's driven by changes in temperature and salinity, which change the density. So this plot here is another schematic. It's obviously more complicated than the one we just looked at, the conveyor belt one. I don't want to go into any of the details here, but what I wanted to do was make sure you realized that the conveyor belt one is a simplification. So what's causing this deep water to return to the surface? Obviously, if all this deep water, this dense water was formed in the North Atlantic and Antarctica, and there was no way of getting it back to the surface, we'd just have the ocean slowly fill up with Antarctic bottom water and North Atlantic deep water, and then we'd end up with this really thin mixed layer on top, which is heated by the sun and deepened slightly by the winds, but it wouldn't be more than a couple of 100 meters deep. So we need some way of bringing this water back to the surface so that the loop can continue again. It's mechanical mixing or turbulent mixing that causes this. So the mixing, the energy goes into moving the water parcels around and making them slightly warmer, and they eventually get back to the surface. So the energy for this mixing comes from a number of different sources: tides, and winds, and even geothermal heating of the ocean.